there was something I was going to go over from last time, but I'll do that at the end because the others won't be able to see the board yet. Okay, so axions in string theory. Quite a bit of selected reading for this. Carroll's book on general relativity, which is available also on the archive, introduces some of the notation that I'll use for a little bit on differential forms, but I'll also try and do an example that doesn't use that notation. The classic on string theory, of course, is Green, Schwartz, Witten. They again introduce some of the notation quite well in chapter 12. For the phenomenology, my review of Anataki et al. And I also like this paper by Andreas Ringwald for a kind of brief introduction to the string theory as well. Find it quite approachable. Okay, so last time we talked about axions in particle physics, and they are, and we described them in terms of a field theory. String theory has two different sources of axions. One is one are so-called matter axions. Matter axions are just like the axions we talked about yesterday, described in terms of field theory, and they come from the open string sector. Okay, right. And then we also have geometric axions. Geometric axions come from the closed string sector. So open strings are to do with matter, closed strings are to do with gravity. The geometric axions are paired up with so-called moduli, which we'll talk about quite a bit through the first part of the lecture. They're not paired up with a complex field like the matter axions were. So our matter axions, if you remember, we had a complex field and we had a radial part of the complex field, and the axion was the phase of this complex field, and it emerged as this approximate global U1 symmetry. The axion was the Goldstone boson. The geometric axions in string theory pair up with the moduli not in this way. There is no spontaneous symmetry breaking. There's no breaking of a continuous global symmetry in 4D, as far as I understand it. I'm going to draw a picture now, which I have seen other people draw, but I haven't found much about it in the literature, about how these two might be related. It might be related by so-called open-closed string duality. So, for example, we can have D branes. Yes, I am recording. Okay. So, for example, we can have D branes, and D branes have strings going between them, open strings, and matter lives on the end of these open strings. This is like the classic QCD picture of strings, where you would have quarks on the end given by the Champerton charges. So type 2D, D branes, open strings, matter lives on the D branes. But at one loop in string theory, which is a string loop, you have this picture where there's an open-closed string duality at one loop. So at one loop, instead of having the one loop open string, we could also imagine the propagation of a closed string that's between the branes, and closed strings moving between branes transmit gravitational forces. So closed strings, gravity, open strings, matter. There could be a relation between the matter and the geometric axions due to this open and closed string duality. I haven't seen much about it in the literature, but it's easy to think of in a picture. Okay, so axions are really generic. It's not just something to do with string theory. There are lots of beyond the standard model theories that would give rise to axions for exactly the same reason. Why is that? So you need extra dimensions. As you know, extra dimensions give you scalar Kaluza-Klein modes. These are the moduli. Again, I'll go over this. Extra dimensions give you scalars in the lower dimensional theory. Supersymmetry demands that you introduce CP-odd partners to your scalars. Things have to live in complex fields. You have a real part and an imaginary part. The real part and the imaginary part are related under C. So you have these CP-odd partners. And this is all the ingredients that you need to get axions in the lower dimensional theory. So, you know, higher dimensional theories of supergravity, any one you want, will give you axions when you compactify it. So you could have, you know, 5D supergravity and 6D supergravity, whatever. And that's all we're using actually to get the axions in string theory that I'll talk about. The low energy effective field theory of string theory or atom theory by low energy EFT, I mean on length scales larger than the string scale, is just 10 or 11 dimensional supergravity. So that's why the axions occur. The questions we're going to be talking about in this lecture is how many, how massive. So let's go to extra dimensions. So if you've done general relativity, or even if you've just done the simple cosmologist's picture of general relativity, you know that gravity is described by a metric tensor. And you know that the entries of the metric tensor are fields. They depend on the space-time coordinates. So for example, and these give the geometry. For example, flat Friedmann-Robertson-Walker. Flat Friedmann-Robertson-Walker, the s squared is minus the t squared plus a squared dx squared. A here is the cosmic scale factor, and it's a field that depends on time. This is a 1 plus 3 dimensional space-time, where the 1 is the dt, and the 3 part is the dx, and the 3 here is flat Euclidean space, has the topology of R3. If we add an extra dimension to this, we can just write that down. If it's in this kind of product form, so let's take Friedmann-Robertson-Walker and a circle. So we've got one extra dimension, and the one extra dimension takes the form of a circle. Now my metric has my field A, the scale factor that controls the size of the flat Euclidean space, and then it has this circle, and the circle has a angular coordinate phi on it, and some radius that depends on time. So my assumption here is that everything really depends on time. Just like in Friedmann, we assume spatial homogeneity and isotropy. I'm assuming homogeneity and isotropy in the extra circle as well. So what does this look like? What does FLW cross S1 look like? So let's look at what happens as we go along in time. We can draw our manifold R3. What's this doing? We lay down some coordinates on it, x, and then we have a scale factor, a of t, that describes the separation between 2 points with a given coordinate x. Then we put our extra manifold on it, S1. I should have my one upstairs. So we lay S1. When we imagine that there's a circle at every point in space along our manifold R3. Then we need to lay down some coordinates and put some scale factor on it. So we lay down a coordinate phi, which is the angle around the circle, and then we give some scale factor, which in this case we can use as the radius of the circle. And these are coordinate traces, just like they were in the case where we wrote FRW this way. So we need an extra field to describe the size of this circle. And it's easy to generalize this description to any product manifold. So for example, M4, where M4 is the 4-dimensional Friedmann equals time, across xd for any d-dimensional manifold that you can on the metric on. So for example, FRW cross x2, where x2 is the sphere. Now it just looks like this, with now r is r squared, the radius of the sphere. The omega squared is around that of the sphere.
Hey Dottie, can you hear me? Something's gone bad with the mic, I think. At least on my end, I can't hear you.
You can't see the bottom.
All right, I can actually understand that.
You can understand what I'm saying?
Yeah, it's the same for me. It sounds a little bit robotic.
Yeah, some noise appeared.
I haven't done anything. I don't know what I can do to make it better.
Dottie, I think that it might have pushed your input to your mic. See, it doesn't sound any close. It doesn't sound any louder.
Okay. I don't know how to fix that. I can try. Let me try it. How did it sound now?
Oh yeah,
So
that's much better.
Yeah, that's much better.
Okay, it switched to the microphone inside the big purple speaker for some reason, which is not very good, rather than this microphone I just bought, to try and make it sound better for you. So I'm going to have to get to talking into the big purple speaker. But we'll just do that for now until I fix it. Next time. I hope that works. Right. Okay, so let's go back to PowerPoint. View. Slideshow. Okay. You're back to the string theory slideshow now, right? And you can all hear me, I presume.
Yeah, I can hear you, but I don't think it's the mic in the purple speaker. I think it's the mic in the computer, just based on how loud it is when you're at different places in the room.
Okay, so it switched to mic in the computer, so I just have to stand here.
Yeah, more or less. Yeah.
Okay, I'll just stand here. That works too. It won't work very well when I walk over to the blackboard and do blackboard stuff, but let's just cross that bridge when we come to it. Okay. So where were we? We were over here. Product manifolds. So we can generalize our description to any product manifold. ds squared minus dt squared plus a squared dx squared, round metric on the sphere. Here's FRW cross S2. So for S2, again, we just need one thing to describe the size of our sphere, but we have two coordinates on it. The d omega squared here is the round metric on the sphere. It has coordinates theta phi, which you're familiar with. So it'd be d theta squared plus sine squared theta d phi squared, for the two polar angles. But it only needs one number to describe the size of S2. This can also generalize to more complicated manifolds with more complicated topology. So for example, consider the torus T2. So topologically, T2 is just S1 cross S1. It's two copies of the circle. What do I mean by that? So here's my topologist's plaything. This is my manifold. And how do I define the torus? Well, I take this my two-dimensional manifold. I take my two sides on it, and I identify this side, the red ones, with each other because my arrows are pointing in the same direction. And I identify these two sides with each other because my blue arrows are pointing in the same direction. This makes a torus. I can then also, if I choose, lay down toroidal coordinates on this manifold, which follow these directions, the distances between my chosen lines, and you get a torus that looks like this. So this is the torus with toroidal coordinates on it. The coordinate phi2 runs around the belly of the donut, and the coordinate phi1 goes round and through the ring. So given that we know the torus is just two copies of the circle, we can easily write down the metric on the torus in toroidal coordinates. This is the metric on the torus in toroidal coordinates. The s squared is minus the t squared plus a squared dx squared plus sigma 1 squared d phi 1 squared plus sigma 2 squared d phi 2 squared. I need two sizes, sigma, to define the sizes of those two different circles. That's just now drawing that onto our toroidal coordinates. Sigma 1 is the size of the circle here, and sigma 2 is the size of the circle. Sigma 1 is the size of the circle going from the middle out through the hole, and sigma 2 is the size of the radius kind of from the middle to the outside. So this description generalizes to more complicated manifolds with different topology. The description is called, in terms of moduli and Betti numbers. So this description generalizes. The number of closed submanifolds of dimension p which we call the number of closed p cycles, is counted by a topological invariant called the p-Betty number. So in our example with the torus, there are two closed loops of dimension 1, the two circles that go around it. So the first Betty number would be 2. First Betty number of closed one-dimensional loops. There are 2 of them. First Betty number is 2. There is also one closed manifold of dimension 2, which wraps the whole outside of the torus. So the second Betty number would be 1. We require one so-called modulus, sigma, to describe each such manifold. Though, of course, not all of those moduli are independent. So again, in the example of the torus, we needed two radii sigma to describe the sizes of the two compact one cycles, the two circles. Then the overall volume of the total of the two-dimensional surface of the torus is described just in terms of these two, and we don't need another modulus to tell us about that. So not all of the moduli are independent. And now I'm going to tell you about the dimensional reduction of the Einstein-Hilbert action, M4 cross S1, and show you that these fields, fields sigma, appear as scalars to us in 4 dimensions. So I'm going to switch to the blackboard. Stop sharing that. And now remote people should be seeing the blackboard in front of you.
Yep, that's fine.
Good. The sound may not be very good, but hopefully you'll be able to read what is going on. Okay, so we're going to dimensionally reduce our theory. So I need to give you a few necessary results in order to do this. So just like last time, I had to tell you the Feynman rules, I had to tell you a few things in order to do the derivation. So we're going to assume that our metric in d dimensions, I use big indices to run over all 0 to d minus 1. This is our metric in d dimensions, and I write it as using this product ansatz as g twiddle, and I'll get rid of the twiddles later. Mu in d minus 1, we're reducing our d-dimensional manifold is n d minus 1 cross S1. And then there are vector perturbations that live here, which I'm going to neglect due to symmetry. And then I'm going to rewrite my modulus that I used before in the following way: e to the 2 sigma. Here, so e to the 2 sigma is dimensionless, so I have some length scale on that manifold, and then it changes in this way. And the vectors are equal to 0 if md minus 1 is FRW by symmetry. I'm not going to consider the usual Kaluza-Klein story where you're interested in these vectors that give you vector fields. I'm going to ignore those by symmetry. And I'm interested in this guy, the scalar. So for such a metric, the Ricci scalar takes the following form. So the Ricci scalar in b dimensions is equal to the Ricci scalar in d minus 1 dimensions minus 2 box e to the 2 sigma over e to the sigma. This is for any conformally flat metric here, and box is box on d minus 1. So, and twiddle refers to that I'm using now the twiddle coordinates here. Okay, so this is the form of the Ricci scalar that we're going to use. And I need to give you another result. which is to do with so-called conformal transformations. So this applies for any conformally flat manifold here, which means that I can just write. So this is any conformally flat X that I can compactify on, and that means that I can write this manifold as just the Euclidean unit metric in some coordinates times some overall scale factor. This is true for S1, as you saw, it's just R squared and phi squared. It's also true for T2. And it is not true, for example, for the sphere, because the sphere has curvature, and that's R squared d theta squared plus sine squared theta d phi squared, not true for the sphere. In relation to string theory, it's also true for what we were talking about, so-called Calabi-Yau manifolds. So this special condition holds in the string theory case too. Okay, so I need to tell you also about so-called conformal transformations. So conformal transformation means that I change the metric by some constant factor. So if I take G twiddle mu,
Sorry, the sigma analysis does it only depend on T or also on spatial coordinates?
in this example, it's only going to depend on T by symmetry. Because I only want to get F or W in the large first. Okay, so conformal transformation is the following. G twiddle mu is equal to e to the minus omega G mu. When you do this, obviously the square root of minus twiddle G, you can work out how this changes the determinant very easily. E to the minus 2 omega square root minus G. This is when the minus 1 is equal to 4. So I'm compactifying actually from a 5D theory down to 4D. This factor 2 is obvious, is the minus 2 over 2, which you should be able to see quite easily. When you do this, I'm going to show you how the Einstein-Hilbert action changes. So this is again a result we're going to have to just use.
Could you please lower the black one?
Yeah, a little bit.
Thank you very much.
Hard to write on these boards. Okay. Under such a transformation, the Einstein-Hilbert action, which is equal to integral d4x square root minus g e to the omega r4. If I have an action that looks like this, and I make that conformal transformation, I get integral d4x square root minus g r. So I get rid of my e to the omega on Ritchie, but then I get extra terms, which are 3 box e to the omega over e to the omega minus 9 over 2 d omega squared. So you should kind of be seeing where the story is going to go here. This is why I've written it in this form e to the 2 sigma. We get these nice changes to the Ritchie scalar, but we can absorb lots of what happens in conformal transformations and end up with kinetic terms for whatever we have to make the conformal transformation with. So this is where we're going. And I'm just going to give you some more details on how that happens. So I'm going to have to rub off these results, but that's because they're on my blackboard, so hopefully you can remember some of them. Hopefully you can just remember what this kind of looks like, believe me, and all the steps that I took. We're not actually going to talk about moduli very much, but it's just easier to see in this set, this way you know what general relativity is, that you get extra fields. And the idea is just, I'll then show you kind of how this generalizes to give you also Axion-like fields. Okay, so what do we start with? So we need our action in 5b, which is equal to d5x, square root minus g5 or 5. The 5d Planck mass squared, 5d Planck mass cubed over 2. Then, okay, what happens here? So now none of the coordinates I wrote down are metric. Depend on x5. No quantities depend on x5, the coordinate on the 5th dimension, which means we can integrate over x5. And what does that mean? The integral the x5 is equal to, I have to have something that has dimensions of length, which I'm going to use the d-dimensional Planck mass, 1 over md. So this just means that I'm measuring the size of my extra dimension in units of the Planck mass. I don't have any other units in this problem, so that's what I'm going to use. In string theory, you would use the string scale here. I integrate from minus pi to pi d theta e to the sigma, which is the size r of that dimension. Okay? So that's what we have to do. So I substitute this into here, and I note also that square root minus g5 is equal to square root minus g tilde, my metric just in the four large dimensions, and e to the sigma. So I need to get my factors of e to the sigma right. I'm going to get one from here and one from here. So I substitute all of this in my Einstein-Hilbert action, and I get s is equal to 2 pi times m star. M star is the d-dimensional, is the 5-dimensional Planck mass, which is not the same as the 4-dimensional Planck mass. We will see how they're related now. 2 pi m star squared over 2 integral d4x square root minus g tilde e to the 2 sigma r 5. I should keep my tildes. Keep my tildes. Remember that we're in tilde coordinates at the moment. And then I just substitute in the result that I said that we needed for that. This is just equal to 2 pi d-dimensional Planck mass squared over 2 integral d4x. This is what people mean when they say dimensional reduction, by the way. They just mean integrate over x5. Okay, nothing mysterious. Square root minus g e to the 2 sigma r24 minus 2 e to the sigma box twiddle e to the sigma. That was our result before. This is called the action in the so-called Jordan frame. So this looks like the Einstein-Hilbert action, but with this conformal factor up front. This is what people refer to as the Jordan frame. And so now we just use our second result about conformal transformations to get rid of this factor and make the first part of this action look like Einstein-Hilbert in 4D. So we just use this result here. make a conformal transformation, get rid of our factor here. So we identify e to the omega equals e to the 2 sigma. And we make a conformal transformation to go to the so-called Einstein frame. It's just a field redefinition now that makes things look canonical in 4D, which is the whole aim of this. But of course, if I had matter around, this conformal transformation changes the metric that the matter interacts with. So the field sigma interacts with the matter, with all matter, due to these conformal transformations, gravitation. Okay, so now we go conformal Einstein. We identify omega equals 2 sigma, and what we're going to do. Okay, so now just transforming this term, I'm forgetting this for the moment. We get that S Einstein is equal to 2 pi m star squared over 2. So we just identify this as black mass squared. Integral e for x squared root minus g r4 minus 9 e sigma squared plus 3 box e to the 2 sigma over e to the 2 sigma. Okay, so now we've got kinetic terms for sigma. What we have to remember is that our conformal transformation will also affect this term in 2 ways. It changes what we mean by box, and it changes square root minus g. So next, to get all of the kinetic terms for sigma together, we have to apply also to, let's call this delta S sigma. Delta S sigma. And I'm going to skip the details in the interest of time, but you can see that you will just end up with a load of terms that look like this and like this. Right? That's intuitively obvious. That's obvious to everybody. You're going to end up with loads of terms that have box and some power of e to the sigma. So we need to deal with those and try and get everything in the form of a canonical kinetic term. And we're going to use I'll just outline the tricks that you use, and then write a kind of general solution. So we have to do integration by parts and apply the chain rule, basically. Integration by parts plus chain rule. For example, 3 box e to the 2 sigma over e to the 2 sigma can be written as 12 e sigma squared plus 6 box sigma. And this term is a total derivative, so this vanishes under integration by parts. So you just do that to every single term that you have, and you end up with, sometimes out the front here, still an e to the n sigma. So you can't get rid of all of the conformal factors. And not all conformal factors vanish, which gives the overall action for sigma takes the form m times squared over 2, the 4D Planck mass now, integral d4x, square root minus g, some function of sigma, d sigma squared. So you have a massless field that only has derivatives with a non-canonical connected term. So you have, and we got this for S1, we got just one of these, and it's obvious that this will generalize. So we can generalize this to, for example, T2, or to any Tn, or to anything that is a product of conformally flat parts. So this is where I want you to see the appearance of the Betti number, the appearance of the topology, the number of fields. So we can generalize. So let's say Rd is equal to R4, and then if our metric G is G mu nu, e to the 2 sigma 1, e to the 2 sigma 2, e to the 2 sigma dot, 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 add any number of conformally flat factors into the metric, then our R will be minus 2 so we need a sigma for each conformal factor in the metric, and then you will now get a generalization of this, because you need to make a series of different conformal transformations. Let's just write down what the Einstein-Hilbert term would look like in this case. You would have S as equal to integral d4x square root minus g tilde. I'll do 10 dimensions, 26. So d-dimensional Planck mass to the 8th power. The volume of your x6 over the string scale to 6. And then you would get exponential 2 1 over I equals 1 to 6 sigma I times R twiddle 4 plus dot dot is the kinetic terms of sigma. So you notice that in this case, so this is M4 cross T6. I have a different conformal factor for each of my sigmas, so I have to make 6 different conformal transformations. And when I do that on box, all of the kinetic terms, all of these different moduli will get mixed up, because box twiddle will have to change each time, and box is 2 derivatives. So all the kinetic terms will get mixed up. And the general form General kinetic matrix, all the sigmas, U sigma I, D, sigma J. So in this example, you would need 6 different sigmas to control 6 different circles on the torus, and the kinetic term is generally mixed up between all of them. That's all I want, and that's all I want to see from this example. You get one, you can get a different contribution here according to the topology of this manifold. And in general, things are messy and you need better notation than we have to deal with it all. Okay, so I'm going to switch back now to my slides. Hopefully that's this one. I'm going over here. Great. Okay, so back to the slides, and hopefully everyone in the other end can hear me better again now, and can see the slides. So let's get back to where we were. Okay, homogeneous manifolds, topology. Here we are, moduli and Betti numbers. And we just learned that these moduli, these things that describe the size of these different cycles on an extra dimensional space, appear as massless scalars in 4 dimensions, but generally with messy kinetic terms, but they're massless. This is
sorry to interrupt, but is it just me, or can the other remote people also not see the slides? I just see like a white slide with a black bar or something.
Yeah, that's the same for me.
Yeah, okay.
Why has it changed what it should be showing? Okay. Let me try something else. Let me stop sharing and try again. It's really confusing. Every time I use it, it seems to be different. Let's try again. Okay. What do you see now?
Yeah, I can see the slides.
In what way do you see them?
Yeah, like in a like small, so not full screen, but maybe.
And now are they big or small?
Yeah, now it's kind of like again a small screen, but just entirely white, so it didn't maximize properly on the screen, or yeah, something like that.
It's a nightmare. What if I bring this over somewhere else? Go away. I can get hold of you. Let's see if it works better if I show it from here. Because I think, what do you see now?
Oh yeah, yeah. Now I can see the slides. Yeah.
From my screen, not from the screen. Okay. And I also have to do this and not presenter view so that you so that you get full screen. Okay, so we just talked about the moduli as 4D scalars on the blackboard, and we talked about how they are massless. This is, of course, a problem for string theory in general, and for any theory with extra dimensions. The moduli are massless, and there's nothing that actually fixes the size of the extra dimensions. There are known ways to fix their size, though. There are ways to give potentials to the moduli. I won't talk about them. But you can give a potential to them, and then that causes them to roll to the bottom of their potential and fixes the extra dimensions to a given size. And this can be done, but it is not an uncontroversial topic. So, When you compactify string theory, though, you have to get rid of 6 dimensions. And there's a lot more you can do than just have a torus. You don't have to just have 6 copies of S1. You can have many, many different types of manifold. But you can limit your choice by demanding some kind of symmetry. By demanding some kind of symmetry of your 4D theory that you want. And this was famously done by Candelas et al., Candelas, Horowitz, Strominger, and Witten in 1985. And they told us that if you want these symmetry conditions, your manifold S6 had better be what is called a Calabi-Yau threefold. So 3, because you have to have complex dimensions. So you have 6 dimensions, but you have to be able to write them in a way that allows you to use complex notation. And what that means is it has to be a complex manifold, such that the metric ds squared can be written as dz bar, where bar is complex conjugation. So there are 3 complex dimensions. It's Calabi-Yau threefold. It's not just complex dimensions. It has to be more than that. It has to be Riemannian and Hermitian, which means it's what's called a Kähler manifold. It has to be Ricci flat, which means it has just one conformal factor out the front there, and the rest is more complicated. And if it satisfies these conditions, you get the things that they wanted. The things they wanted were, first of all, what we definitely have to have, chiral fermions. So we know that the electroweak interaction is distinguished between left and right-handed fermions. Famously, CP violation in chaos interactions. So you better have chiral fermions. You have to get that. Then they also demanded that they get only minimal supersymmetry in 4 dimensions. So string theory is maximally supersymmetric, which in 4D would be n equals 8 supersymmetry, I think. But they demanded that you only got one of those supersymmetries down in the 4 dimensions. And then you have to later break that with spontaneous symmetry breaking, for example. So of course you don't necessarily have to have this condition, but supersymmetry generally makes people's computational life easier, so that's why people do this. So this tells you that you have to have what's called a Calabi-Yau threefold. There's an equivalent set of statements for M theory. M theory has 7 dimensions, so you can compactify on a 7-dimensional manifold. So it can't be Calabi-Yau because 7 is not even, so it can't be complex. But the equivalent statement is that these manifolds have to have what's called G2 holonomy. But it's a lot harder to know about these things because they don't have all the nice complex structure. They can't write things in this dz bar way. So M theory is harder in this sense. This is a picture of a projection of a Calabi-Yau manifold on that you can get on Wikipedia. Of course, lots is known about these things, and people like to show these pretty pictures. I don't know if anyone learns anything from them. But this is a 3D projection of one. This is a movie that you can find on YouTube. So a generalization of my picture with the circles. Okay, here's each point in space. You've got your Calabi-Yau manifold. They're rotating it for you and showing you what it looks like under rotation at those different points. There's also an album called Calabi-Yau Space by a band called Doppler Effect. It actually has a track on it called Holomorphic N0 form, and we will briefly mention those later. So you can hear about what all of these things sound like. You can also listen to Calabi-Yau manifolds if you want to. Okay. So, whence axions though? Why all this? Like where are we going here? Where are the axions going to come from? Well, the point is that the moduli come from the metric. I showed you what happens to the metric. We have to have something else to give us other degrees of freedom apart from the metric, i.e. the axions. And a simple way to kind of see why you should have extra fields in string theory other than just the metric is that in string theory, the native thing that you have is actually the coordinates x with subscript m, big M lives in all the d dimensions. So if I make a tensor xm, xn, that has no particular symmetry properties. And from that, I can make the metric tensor, which is symmetric. I can have a scalar trace called the dilaton, but I can also have an anti-symmetric part. So this has no particular symmetry, x. So I have a symmetric part, G, the metric, and an anti-symmetric part, B, which is a so-called two-form. So you always have in string theory at least these extra fields on top of the metric. The scalar dilaton and the anti-symmetric two-form. All string theories contain these fields, and we also have to do this game of dimensional reduction on these fields here. So these give us additional degrees of freedom on top of the moduli in 4D. But of course, there isn't just one type of string theory. So I said all string theories have these fields. What else you have depends on where you are in the web of string dualities. So this is a nice figure from the PhD thesis of Rhiannon Gwynn. So she's showing this, the parable of the elephant. So first of all, okay, you know that there are these 5 different types of string theory: type 2A, type 2B, type 1, heterotic E88, and heterotic SO32. And they are all related via dualities, T dualities, S dualities, things like this. And they're supposed to all be one manifestation of this thing called M theory. So the parable here is a parable, I think, in Indian mythology. And there are all these old blind men, and they're standing around an elephant, and they say, that they describe, like what are we seeing here? So one of them is feeling the legs, and he goes, right, it's a tree, definitely a tree. And the other guy is like, he's feeling the nose, and he goes, no man, it's a snake, we need to run away. The other guy is like feeling the tail, and he's like, I think it's a horse. So like, they're all very confused because none of them can see the bigger picture that it's actually an elephant. And so how can we get anything general from this about getting axions in 4 dimensions? So now I'm reminded of a quote, well, not a quote, a quotation by the Zen master Dogen from the 13th century. So Dogen said, do not spend so much time rubbing only a part of the elephant. Look inwards and advance directly along the road that leads to the mind. So we are going to try and find out what is common about all of these. This picture here is a Buddha in my favorite of the mudras, and he's got his hand on the floor. He's touching the floor here, and this is what happened when the Buddha achieved enlightenment for the first time, sitting under the Bodhi tree. He touched the floor afterwards to ground himself in reality. After being on some esoteric journey, touched the floor, grounding in reality. So we're going to try and pick out the common thing to all of these different string theories and find something that is grounded in reality that we can get some phenomenology out of. And that thing is P-form fields. This is what is going to be common to all of these string theories. So they're all described in the low energy limit by supergravity with extra dimensions. And as well as this model independent thing, BMN, is two-form, all the different string theories in M theory contain different anti-symmetric P-form fields in the effective field theory. So what are they? So for example, they're things with higher numbers of indices. So for example, 10-dimensional type 2D supergravity has a 4-form field, a thing with 4 indices. 11-dimensional supergravity, what we describe M theory, has a 3-form field, a thing with 3 indices. And compactification of a P-form, just like compactifying the metric gave us scalar moduli, compactification of P-forms gives us CP odd scalars, which so pseudoscalars, which end up pairing up the moduli into supermultiplets. And it's these partners, these things that come from compactification of P-forms that string theorists call axions. So they are CP odd scalars, And it turns out that they have the right symmetry properties to couple to things like GG dual that we saw last time as well. So they're not just pseudoscalars, they have approximate shift symmetries, and they couple to topological terms in the action, things like GG dual. So string theorists call all of these things axions. They don't have to solve the strong CP problem, but they're all axions, and they're grounded in reality because they end up being light and they end up having cosmological consequences. And that's what we're going to be doing for the rest of the course, is looking for phenomenological consequences, things that we can search for in the sky and on Earth of these general things that you always get from string theory. So what are p-form fields? So this is where I'm going to use for a little bit some notation you probably haven't seen before, for which I point you to Carroll's book on GR, chapters 1 and 2. They're also introduced in Green, Schwartz, Witten. There's a nice chapter on them, whatever chapter I referred to in the beginning in the reading, I think chapter 8 in GSW2. There's also an introduction in Becker Schwartz that is quite good, and one of the appendices, I think. So, and Viraf has also kindly prepared some notes on this, and also on what I'll do in the next slides as well, which I think you'll put.
Yeah, I mean, I can just send it to you, and then
I'll put them on StudIP with the with these slides. So p-form fields are a generalization of the Maxwell stress energy to things with more indices. So they're anti-symmetric and gauge invariant. So F mu nu, for example, is a two-form, anti-symmetric. F mu nu is minus F u nu. That's just from its definition in terms of the derivatives of the vector potential. So F mu nu is d mu a mu minus d mu a mu. So that is obviously anti-symmetric under exchange of indices. And it's gauge invariant. It's invariant under the shift of A by any derivative. So gauge invariant, I mean A goes to A plus d mu lambda, because the partial derivative commute, this is automatically gauge invariant as well. So forms are anti-symmetric and gauge invariant. F is a two-form, this is what I just said, and it's made from the one form A. So F mu nu is d mu a mu minus d mu a mu. So F is a two-form, and we write this as exterior derivative, this funny operator D, acting on the one form A1. So exterior derivatives raise the number of indices and return a P form into a P plus one form. That's the exterior derivative. We can make an action for the field A using F. So we can make a quadratic action that's gauge invariant and will give us the right equations of motion. This action here, that we know, the Maxwell action, b4x square root minus g f squared, b4x ff dual. We can write this using this notation of forms as f wedge star f plus f wedge f. See the things. The metric appears on the gauge kinetic term here. There is no metric on the topological Chern-Simons term. These things here are wedge products and Hodge stars, and I don't have to write b4x on these integrals because the differentials are contained in the definition of f. So they're written down as things ready to be integrated over. So it saves you on a lot of notation. And the star, the Hodge star, is the thing that knows about the metric. So the action for a p-form field A follows the same rules as Maxwell. So fp plus 1 is dap. So I get an action for AP as fp plus 1 wedge star fp plus 1. That would be the usual Maxwell kinetic term. Because I have written my p plus 1 form as an exterior derivative of a p form, we say that f is exact. Then the equation of motion with the anti-identities, which follow from this action, can be written in the following way: df equals 0, d star f equals 0. This is the Bianchi identity, and this is the equation of motion. This is the way that string theorists and people like them write Maxwell's equations. I went to undergraduate university in Edinburgh, and we had the James Clerk Maxwell building. And in honor of some birthday of his, they wanted to print Maxwell's equations on the floor. And apparently the arguments in the staff meeting over what form they should write them in went on for a long time. Integral form, differential form, or using differential forms like this. And in the end, they wrote all of them. So on the floor of the James Clerk Maxwell building in Edinburgh, this is one of the ways you can see Maxwell's equations written. This is of course source free, and there should be a current on this side as well. So this, the Bianchi identity, that says that f is closed, df equals 0. Because f is exact, because f equals dA, Bianchi identity follows actually by construction, because this exterior derivative operator always satisfies d squared equals 0. If A is also exact, if we can write A, so like in the Maxwell case, if I can write A mu as a pure gauge term, d mu lambda, if I can write AP as equal to d lambda p minus 1, A was also exact, but it's not. But this field configuration would not be physical. It would be pure gauge. So you could just get rid of it by an appropriate choice of gauge. So a physical solution requires A to be closed, but not exact. So it requires dA to equal, it requires, what does it require? It requires dA to equal 0. It requires f equals dA equals 0 for a 0 mode. But A does not equal d lambda. So physical 0 modes require closed but not exact forms. Why on earth have I told you this? I have told you this because now we can use a bit of machinery and some results from mathematics. So we need to look for 0 modes of A. We want to know what happens when we compactify this P form and find 0 modes with respect to the compact coordinates. There are a special class of forms called harmonic forms omega, which is they are a complete basis. So if we write our solution as a sum of these harmonic forms with general coefficients, it will just be a general solution. You haven't made any assumption about what the solution is. But it makes your life easier because the harmonic forms are the basis of closed but not exact forms on a given manifold. So they are the basis, they're like the photons. They're the basis that will give you just the information you need about physical 0 mode solutions, physical vacuum solutions. So that's what we do. We write our P form AP as an expansion in terms of the harmonic forms, omega, with any general coefficient. We've separated variables because of the symmetry of our manifold, and any coefficient A with any dependence on so the coordinates X are coordinates in the large dimensions and Y are the coordinates in the compact dimensions. I can have my coefficients take any value. So these things, omega P, are like the photons living on the compact manifold. And then the AI are the intensity, are how many of each different polarization of photon, if you like, are there living on the compact manifold. But to us, it just looks like a scalar function, A, the intensity, the amount of energy density in that photon. The key thing here is, what does that sum extend to? The sum contains BP, i.e. the P Betti number that we talked about before, number of terms. There is one harmonic form for each closed P. There is one harmonic form of type P, so P indices, for each closed P cycle on your manifold. This is a topological result. So that means that on our torus, there are 2 harmonic 1 forms for the 2 circles around it, and 1 harmonic 2 form for the overall surface. And these coefficients A, you can get from just inverting this relationship. The A's are the integral of the form P around the closed cycle C, around each closed cycle I. So it's the amount, it's the Wilson line, if you want to use the jargon, the integral of AP around the closed cycle CP. Around closed cycle of dimension P, label I. That's what A tells you. It tells you how much of the photon is there around that closed cycle. And these are the axions. So, and the kinetic term for these axions comes from the Maxwell action for the form AP. So just like the kinetic terms for our moduli came from the Einstein-Hilbert term, the kinetic terms for the axions come from the Maxwell term of these P-form fields. So now I'm going to do just quickly on the blackboard an example of this on the torus T2, which happens to also be a Calabi-Yau one-fold. Is it the only Calabi-Yau one-fold?
It's the only compact Calabi-Yau one-fold.
The only compact Calabi-Yau one-fold. Okay, so I'm going to quickly sketch something about compactifying a one form on T2 and try and let you see how we get two extra fields, the two axions to describe it. So the photons, so these aren't, I'm saying photon because it's like a photon, but I'm not saying that this is U1 like the physical photon. So I haven't written down the Maxwell action for the actual, physical standard model photon. I'm just calling these things photons. They're like generalizations thereof. Okay, so I'm going to stop sharing a minute. So we go back to Blackboard. And I'm going to just quickly show you what I mean for compactification of a one form on T2. There are a lot more details about this and more in the notes that I've just prepared. We tried very hard to make this as simple as possible, but there's only so far you can go with using component notation and showing things explicitly without using all of this weird differential forms notation. I'll try and do this without that notation now. So we're going to compactify AM, a one form in D dimensions, on T2. In order that everything happens nice and easily, I'm going to work just at the level of the equations of motion after gauge fixing. So we know the equation of motion that we have to get from the Maxwell action after gauge fixing, or in a particular gauge, is just box D, where D is the D-dimensional box operator, acting on AM equals 0. Vacuum. This is after gauge fixing. We have this product metric, and that's, so we're compactifying M D minus 2 cross T2 as our manifold. So what we know is that, and we also know that box factorizes. And box D is equal to box M plus box T2. So what we're going to do is decompose AM into a general solution that satisfies our symmetry requirements. We're not going to assume anything about what AM is doing on the compact manifold because we can't see it, but we're going to assume homogeneity and isotropy in M. So the general solution that looks like that is the sum over I AI of x, omega index small n, where the small Roman indices only run in the large directions, so n equals okay, so let's make this actually 8, so mean is 0 to 7, and small is 8. The small is only going to come back financial instruments. Why? I'm not getting that. Symmetry. Homology is an isotropic. Large dimensions, a vector with actually large scale magnetic field through a universal dynamic energy. And finish. Doing this on the torus is I can write down for you what the basis of harmonic of the omega is, and just show you what happens at the level of the equations of motion. 15 minutes left. Good. Okay, so omega mi, what is omega mi? It's proportional to some polarization vector, epsilon m, the photon-like thing, e to the I n phi 1 over r1, where these are our toroidal coordinates from before. Where r1 is equal to the string length and e to the sigma, where sigma is our modulus. We always require our any distance in this case to be larger than the string scale, because otherwise the effective field theory that we're assuming would not be valid. So this thing sigma had better be larger than 1. Okay, or I suppose 0 the way I've written it here. Okay. So these omega m are like photons, kind of like photons on T2, and A are the intensity thereon. So what do the equations of motion look like? We just substitute this in. Box T AM equals omega sum over I omega box A plus A omega box MA plus A box T2 omega. Box T2 only acts on the y coordinates, box M only acts on the x coordinates. For these, box is identically 0, so it automatically satisfies the equations of motion. So then we just get sum over I, omega I, y, box x equals 0. The omegas are non-zero, so we can divide them off. So this ni is just equal to 1 and 2. We've just done the T2. There are just two coordinates. So omega 1, omega 2 do the same. So we just get two equations of motion. Box M A1 equals 0, and box M A2 equals 0. two massless axions and 40, or rather actually in this example, 80. Couldn't have to 5 and 10 times 8 on a P2. So we've done this at the level of the equations of motion, but the action has to be invariant under field redefinitions, and the field redefinitions that the action has to be invariant under follow from the gauge invariance of F. So we have, or rather the gauge invariance of A, we have to be able to make a shift of A by any gauge parameter, lambda. We have to go A mu goes to A mu plus D mu lambda. And these equations of motion that I have written are in one particular gauge and thus one particular choice of coordinates on field space. So the general L must be field redefinition invariant from the gauge symmetry of A, which implies that we need a metric for field space. So the Lagrangian, or rather the action, B minus 2x has to have a metric on field space. It's invariant under field redefinitions. So the action that would give rise to two equations of motion in general has to have this field redefinition invariance. This thing we'll come back to. It's something that you have to compute. You generally look up in a textbook. And it's called the Taylor metric. And it will be a function of the moduli. So we're going to come back to it. So hopefully you've seen how you can get two axions from compactifying the one form on a T2. And now we'll go back to the slides. So which one are you? This one. Brilliant. Everyone back with the slides?
Yep.
Good. Okay. So we've just compactified T2 on CY1. And for more details, see the notes by there. Now we'll move on. So how many axions are there? What are the Betti numbers of Calabi-Yau manifolds? Fortunately, lots is known about this. Calabi-Yau manifolds are studied to death. So for Calabi-Yau threefolds, all the Betti numbers can be computed from just two so-called Hodge numbers, H11 and H12. They are known for a huge database of Calabi-Yau manifolds. So this is the famous Kreuzer-Skarka database. So Kreuzer and Skarka constructed all reflexive polytopes in 4 dimensions and used these to just like we know all of the Platonic solids in 3 dimensions. If you get all the reflexive polytopes in 4 dimensions, you can construct the Hodge numbers of all Calabi-Yau threefolds. And this is the distribution of those. So these are the two Hodge numbers, H11, H12, and the color scale here represents the frequency of occurrence of that Hodge number in their list. So at the peak here, there are 10 to the 6 or so polytopes with a particular value of H11. H12, the peak is where H11 equals H12 is of order 25. The Betti numbers are of order, the Hodge numbers, there's some sum of them. Which one you need is different for different string theories. We'll talk about it in a minute. But you typically get a number of axions of order H11 today. In type 2b, the number of axions is H11 from the compactification of the C4 form. So if you drew a polytope at random, you would get if the universe worked as here's a random manifold at the beginning of the universe, then, well, if the universe worked like here's a random polytope at the beginning of the universe, you would expect to just get one with about 25 axions. It turns out that there are actually many manifolds for each polytope, for reasons that I don't really understand, called to do with triangulations of that polytope. If you drew a manifold at random, you would be overwhelmingly likely to draw a manifold with h on 1 equals 471. Is it 471? 491, the largest h on 1 in the list. So if the universe just worked by giving you random manifolds, you would expect either 500 or say 25 axions, but certainly a number larger than 1. Right? Many axions. It's very possible to have lots of them. So, okay, this is the notable feature about this distribution, a famous thing called mirror symmetry. Okay, what happens in type 2B string theory then? The reason I want to labor through this in a little bit more detail to try and give you a sense of what the axion masses and decay constants are. We haven't said anything about that yet. I've just counted them. So how do they scale? So 10-dimensional type 2D supergravity contains a 4-form field, C4. The action for the 4-form field can be written from its 5-form field strength, H5 wedge star H5. 10-dimensional fields, 10-dimensional coordinates. We apply that expansion into the harmonic basis on X6, and we get S is proportional to DAI, KIJ, wedge star, DAJ. 4-dimensional fields, A is a 4-dimensional field, the axion. We have this thing in the calorimetric. The number of axions in this example is given by the 4th Betti number, because we're compactifying a 4 form, which, if you look it up in Becker-Schwarz, B4 is H11. So type 2B supergravity gives you H11 of these so-called model-dependent axions from C4. What is KIJ? KIJ is the kinetic term, the calorimetric. It comes from the conformal transformations and the gauge invariance and such. And it is related, it is written like this in terms of the moduli. And this function K, this scalar function K. K is what's called the Kähler potential, and it has to be computed. And you look it up in Becker-Schwarz for type 2B supergravity, and this is what it is. The true level Kähler potential. So it's just what you would compute from doing those field redefinitions and like the conformal transformations that we did for a compactification of FLW cross S1. We got this kinetic term for the moduli that you can derive. This is just what you get doing the same thing. Minus 2, so it has these parts, the volume, the axiodilaton, and the complex structure moduli. The volume is the important bit for us here. The volume contains information on the Kähler moduli sigma. V can be written in this way. It's a Calabi-Yau threefold, so we need 3 moduli in the volume. Ti, Tj, Tk. It's some triple intersection number. Tells us how we compute the volume from the moduli. These things can be computed for every polytope in that Kreuzer-Skarka database. And the T's are related to the sigmas that we had before. Sigma is the volume of the cycle Ci, and it's the derivative of V with respect to Ti. So parametrically, it should be clear to you that the calorimetric goes like m Planck squared over sigma squared. Why is that? Planck scale is the only mass scale in the problem, it's quantum gravity. And this thing has to have mass dimension 2, because the A fields I'm using in this example are dimensionless. They're like the theta field that we had in the last lecture. No decay constant. This is the key. Sigma is also dimensionless because it's just a conformal factor. And I've taken 2 derivatives of something that has mass dimension 2 with respect to sigma. So it has to go like m Planck squared over sigma squared. The sigmas are the volumes of the cycles. So they better be larger than 1 in string units. So the entries of this thing had better be smaller than the Planck scale square, you know, by order of magnitude. So, you know, like this is what I said just now, like sigma, the fields are dimensionless. So we can diagonalize this metric K. So in the Lagrangian, instead of being Kij, dA, I, dAj, like I wrote on the board before, I can diagonalize K and I just get the eigenvectors, the eigenvalues of K times dA squared. The eigenvectors of K, eigenvalues of K are the decay constants. This is our Lagrangian like we had before for the axiom, f squared d theta squared. So this tells us the first important result that we learned. The decay constants scale like 1 over n Planck over sigma. Sigma had better be larger than 1. We've only got 5 minutes, so I'm going to try and go a little bit faster through the last bit. Axion masses. How did our axion get mass before? The axion mass before got mass before from QCD becoming strongly coupled. You can get things like QCD, type 2D string theory, from a stack of D7 branes. The D7 branes have to get rid of 4 of their dimensions so that 3 of them fill our space. So we wrap them on 4 cycles. A stack of ND7 branes gives you a gauge group with gives you a gauge theory with gauge group UN. UN is U1 cross SUN. And the 4D gauge group has the following action, the Maxwell term and the topological term. This can give you instantons that will give you mass to your axions. And the coupling constants are fixed by the modulus in the axiom. Theta is just A, G squared is 1 over sigma. The instanton action, which is the thing that controls the topological susceptibility, scales like 8 pi over G squared, so it goes like sigma. And the axion masses go like e to the minus s. These are things that you can just look up for gauge theory in 4D. So we learn that the axion mass squared goes like e to the minus modulus. So you can change the modulus by just a small amount, and the axion masses will change a lot. But the decay constants will not change a lot. The decay constants have a narrower distribution than the masses. The masses are hierarchically separated for all your different axions. Okay, here's a simple example. The axion mass could be written as m Planck squared m Suzy squared e to the minus sigma. Fa is m Planck over sigma. We take Suzy to be broken at 100 TeV. Pick our volume of our cycle larger than 1 or 100. This gives you the right gut scale coupling in some example. The axion mass would be 10 to the minus 20 electron volts, and the decay constant would be 10 to the 16 GeV. Value of sigma is close to getting the gut scale right, gut scale coupling for the standard model. As you will see, this shows the parameters, gives us about the right dark matter abundance, and has all the fuzzy dark matter phenomenology that you hear about from the end. You can generalize this. I'm just going to give 2 examples of how you can do better than just those scaling arguments. One is to take a general matrix approach. This is our general axiom now with mass from some non-perturbative effects. Could be gauge groups, could be gravitational instantons, whatever. There's loads of stuff around. And some general K. You can always diagonalize two matrices simultaneously. So you can just look this up for like classical field theory and Goldstein. The 2 matrices can always be simultaneously diagonalized. So the masses and decay constants of our axions here can just be computed from the eigenvalue spectrum of K and M. If there's a large number of axions, where large only has to really be 10 here for it to work, the eigenvalues of these things don't care about what the matrices actually are, due to generalizations of the central limit theorem that come from what's called random matrix theory. So just like in the central limit theorem, you only put in 1 parameter and everything falls out on a Gaussian with that spread. But eigenvalues of random matrices are a similar result, and they all follow from something called the bigger semicircle law. So we need to specify the particular distribution it takes, depends on the form that these matrices take. For example, we might write Kij as AA transpose for 2 matrices A. If A is any rectangular real matrix, then this guarantees that K has positive eigenvalues, which means that we have canonical kinetic terms. I always have a minus sign because I have a mostly positive metric signature. In this case, K is what's called the Wishart matrix with a known eigenvalue spectrum. So if you do random matrix models, you can compute the spectrum of the K constants. Here we did 3 different types of random matrices, and they have different shapes for the distribution of F over M1. The offset here is just arbitrary, and the colors are for different parameters within that class. You can also compute the masses in that case. This is what you would get. You get a kind of log normal distribution for the masses controlled by some parameter in the model, which in this case was the volume of the Calabi-Yau. Sorry, the volume of the G2 manifold. You can even do a little bit better and construct things really explicitly from that Crozer-Skarka database, and this is the last thing I'm going to show you, just to give you an example. You can use all of this machinery and get things pretty explicit. This is the Crozer-Skarka Axions paper by the Mertas et al. The McAllister's group at Cornell. So they scanned this database and construct triple intersection numbers. They construct the moduli space, and they bound the moduli to live in some special place. They don't stabilize them, they just put them at a special place called the identification code. And then they have everything. They have the full axion potential. They have not just for these closed string axions, not the QCD axion. They have the full axion potential in terms of its cosines. They're assuming dilute instanton gas, remember from last time. They know these matrices Q, these instanton charge matrices from the triple intersection numbers. They know this full potential, and they can compute for each value of the Hodge number H11 the distribution of axion masses for all the different manifolds of that H11, sorry, all the different polytopes, and within those polytopes, all the different triangulations. And it's a huge database, they can't do all of it, they just do some sampling of it, and this is what we see. This is the mass of the lightest axion in natural logarithm in terms of the string scale. And the lightest axion, they have lots of them that are very, very light. And in terms of the last modulus, the axion masses, the smallest ones are as light as the 10 to the minus 104 electron volts. So really massless even from a cosmologist point of view, where Hubble is 10 to the minus 33 electron volts to scale. And they can also compute the decay constants, which is from the size of the axion moduli space. This is the log of the size of that space in Planck units. The decay constants, as you go to larger and larger H11, fall lower and lower below the Planck scale, but not much below the Planck scale. And this is 10 to the minus 2, it's 10 to 16 GeV, 10 to the 14 GeV. Small, but not very small. Maybe this distribution is flattening off. So you can really compute a huge amount using these things. And that is all I wanted to say today. So tomorrow, we're done with highfalutin theory, and we're going to start computing dark matter relic densities and doing some phenomenology. So see you all tomorrow.
All right, thank you. See you.